Great. Welcome everyone back. If you're at the second lecture, that means you're truly committed, which is great. So in the first lecture, we introduced CFT, and we gave some basic constraints of conformal symmetry on correlation functions. But we did not really talk about quantum CFT so much. Most of what we were doing was classical kinematics. We spoke about correlation functions, but we didn't actually specify the quantization scheme we were using, because for these basic symmetry constraints, that is not necessary. But a lot of the advantage of conformal symmetry is actually when you can learn about quantum things like operators and unitarity bounds and stuff like that. So that is what is going to be the focus of today's lecture. And so today's lecture, we're going to start with these quantum aspects of CFT, and by the end, we will discuss how to compute conformal blocks, which are the kind of practical vehicle you use in order to do conformal bootstrap. Great. So that's the theme of today's talk, quantum CFT. And so let's begin by just reviewing what we mean by quantization. So let's imagine that we're just working in standard Lorentzian flat space. So we say we have one time direction, r, and then d minus 1 flat directions, for a total of d-dimensional flat space. So how do we quantize the system? So first of all, you have to choose a time direction, which we could choose to be time in this example. So here's time. And then for all the parts of your space-time, which are kind of orthogonal to the time direction, these will be the slices. So in this context, these will all just be a bunch of flat d minus 1 slices. And so the idea is that you define operators. So an operator is defined at a specific point in space and time. So just to be clear, let's write t and x. But then you can also define states, which are at so say this is a state O, and this state is defined for the entire spatial slice for the given time. And so a priori, operators and states are very different, because the operator is defined at one point, where the state is defined along the entire spatial slice. Now, this is kind of the familiar way you've probably seen of quantizing a system. And then, and one advantage of why you choose this slicing is because you want to preserve as much of the symmetry of the system as possible. So if you're dealing with just flat space, you just have translational symmetry. Then the nice thing about this slicing is that these slices will preserve the translational symmetry, this rd minus 1 direction. So for instance, you can move along this time direction using your usual Hamiltonian operator. So e to the I ht, where h is the Hamiltonian. And then states can be labeled by their energy momentum. So if you act with the generator space-time translations, p mu, as we defined in the previous lecture, let's label a state k, which is its momentum. And so this will just give an eigenvalue, k mu for this state k. And so that is the advantage of this standard slicing that people traditionally use. And then you go from space-time time point to time point using the Hamilton. But one thing I want to emphasize is that in some sense, this is just a choice. You can choose to quantize a system in any which way. So you didn't have to choose your spatial slices like this. You could have chosen other slices. And it will turn out that for conformal field theories, there is a better choice. One last comment is that for most of these lectures, we talk about Euclidean CFT. Right now, I'm talking about a Lorentzian quantum field theory, and for a couple points in this lecture where it's kind of useful to use the Lorentzian formalism, I will emphasize it. But in general, you can kind of go back and forth, just in the usual way by making time imaginary. And so, like, once you have your choice of quantization, you can then also apply it to Euclidean subject. Okay, so this is the standard quantization people use for generic quantum field theory. But now I'm going to describe one that's more useful for a scale invariant quantum field theory. So basically our strategy is that we want to choose some slicing which will preserve the greatest amount of symmetry. And so now we have these additional symmetries for conformal field theory, which remember was inversion and scaling. And so a choice of slicing which is better if you want to preserve scaling is to define, okay, so let's think of some spherical setup. So these are, I guess, concentric spheres. And then our time direction is going to be the radius out from the center of this sphere. And then each slice will just be one of these spheres. So it will be a slice sd minus 1. And so our total thing is basically the radial direction r cross SD minus 1 for each slice. So in analogy to here, so here you move through time using the Hamiltonian. Here, you move through these radiuses using the dilation operator. Where I'm not putting an I just because it's not really useful in this context. So remember the dilation operator dilates you, and so it moves you, from one sphere to another sphere. So this is kind of our analog of time. And then
sorry, are we on Lorentzian or are you clearing space now?
So I'm being a little dodgy going back and forth. So for simplicity, I'm just talking about Euclidean here. There I was supposed to talk about the Lorentzian, but you could have done Euclidean by making T Euclidean. And then the advantage of this slicing is that now, for a given state, if we act with our dilation operator, then it diagonalizes it, so you just get the scaling dimension for this operator, labeled by delta. And another advantage is that it also preserves SOD rotations. Because each slice, each sphere SD minus 1 has this rotation group. And so that means you can also, when you act with the generators of rotations, mu nu, which you should hopefully remember from the previous lecture, you also get a simple action, which is given by this matrix S mu nu, where S mu nu implements transformations under rotations for a given symmetry.
Sorry, can I ask another question?
Sure.
So you don't care about the T to minus T symmetry?
T to minus T? We're actually going to talk about that in a little bit. So I'll get to conjugation in a moment. So this S is some matrix. You'll have a different matrix depending on the representation under this rotation group. And so you can see just like this is a more natural quantization, basically because it diagonalizes the dilation operator, and we don't care so much about translations in this context. So to give an example, so we have a vacuum state, which we'll just call 0, and the definition of the state, first of all, it's a singlet under rotations, and then also when you act with the dilation operator, it just gives 0, because this has scaling dimension 1. So that is the simplest state in theory, which is the vacuum. The first nice thing we can learn from our choice of quantization for conformal field theories is what's called the state operator correspondence. So as I mentioned before, for a general quantum field theory, operators and states are very different, because an operator is defined at just one space-time point, where a state is defined on a whole spatial slice. But specifically for conformal field theories, there's actually a one-to-one correspondence between them, and that's because you have this dilation symmetry. And so it's most conveniently seen in this choice of quantization. So in particular, let's take an operator O, defined at the origin, and this has a given scaling dimension delta. And so the claim is that there's a correspondence between this operator and the operator O acting on the vacuum, which we just defined. And so this thing we just defined as a new state labeled phi O. And so this is a one-to-one correspondence. So just as a check that this satisfies the expected definition, i.e. here, what a good well-defined operator should be in this quantization. So let's act on this operator O with the dilation generator. So this is just definition of the operator. We can turn this into a commutator. So the vacuum. And then finally, this thing is just 0, because remember, dilation acting on the vacuum is 0. And then this thing, if you just take the definition of the commutation relations from our previous lecture, you know that it just gives delta times the operator. And so, as promised, this definition of how you get an operator from a state satisfies the expected axioms of what a good state should be in this quantization of our conformal field.
Shai, in this expression,
yes.
Where are you defining the vacuum state? In which Hilbert space? Associated which? Are you talking about Hilbert space associated with a sphere?
Yeah, so here. So I was defining the vacuum that the dilation acting on it is 0.
Okay, but if you choose a particular sphere,
Yeah.
This O, usually I would think that you can only acclimate with operator outside the sphere. It's not clear to me, at least in Euclidean signature, what it means to have operator acting from inside the sphere.
Sorry, but I mean, like,
Just by the usual rule, right? If I'm given, well, all I'm complaining about is that if you really mean O at origin in this left picture,
yeah.
you cannot, that's not a well-defined operator acting on general state in Hilbert space associated with the sphere. You're only allowed to use stuff outside, you're not allowed to use stuff inside.
Okay, so I guess you're saying I should say that it should be slightly outside of wherever the origin of the sphere is.
I would have stated slightly differently. I would have said that you simply identify the space of operators at origin with a subset of states in the Hilbert state on sphere, and I would define its property essentially via how the D and so forth acting on the
Sorry, but what's the difference between that?
The difference is that I would have erased the O0 acting on 0, which is just said that O at 0 corresponds to the state, period. I wouldn't bother writing this thing out in a vacuum. I think that's a bit of I mean, I think can be made sense, but not quite obviously in a way.
Can you be more precise then about how it corresponds to a state?
Yes, the statement is that there's a one, if you, for every local operator inserted in origin, there's a corresponding state on the sphere. We can define the property of that state through, let's say, correlators with this operator. That is, the overlap of this state with any other state is calculated, or the basis element between the state and any other state with some operator inserted is calculated by this Euclidean correlator where you insert O at origin and whatever other operator you sprinkle around the sphere outside.
Yeah, but I do think it is standard to identify the state O with the operator with the on the acting back. Right. I mean, perhaps you have to be a bit careful when you do that, but I do think that is the standard.
I think there's a way to make sense, but it's not very obvious from this picture we're drawing, because
No.
all I'm saying is that O at 0 cannot quite be viewed as a well-defined operator acting on a generic state in the Hilbert space.
Anyways,
But
okay.
I think the limiting procedure actually is correct. That is, if you take O outside the sphere, and if you take O at a point X outside the sphere, that can act on any state of the sphere and produce a new state. That's well defined, and then you can take the limit of that point going to the origin, at the same time shrinking that sphere also to zero size.
Anyway, okay, so thank you for the clarification. So now we're going to talk about conjugation, which I think responds to a question Lisa asked a few minutes ago. So in the standard unitary Lorentzian quantum field theory, using the standard quantization of just R plus RD minus 1 that we discussed before, all space-time generators G are Hermitian operators, so they generate unitary transformations, written in the usual way just by exponentiating G, and by convention put in I, so it'd be Hermitian. So this should preserve the positivity of correlation functions. So for instance, imagine we have some operator defined at the origin, so 0, 0, this is 0 for time, 0 for space. And so if we wanted to find another operator at some time t in position x, in terms of this operator at the origin, then we would act on it with the generator of translations through time as well as space in the usual way. So again, I'm talking about this just standard relativistic quantum field theory here. So you have your Hamiltonian, P0, times time with an I, and then you would have the spatial here times the generators of momentum. Then you have the operator at 0 space and time, and then you have the conjugate of that. So you can now see that because this guy is Hermitian and these operators are Hermitian, thus this quantity for time t in position x is also Hermitian. Because when you conjugate, it changes the signs of these i's, but it also reverses the order of the operators. So everything is Hermitian as you want. So this is in Lorentzian relativistic space. Now, let's imagine we go to Euclidean space. Again, just for a relativistic quantum field theory. And so the way you do that is you define a Euclidean time, TE, just to be minus I times the original time. And then you define your Euclidean operator, just a scalar operator for simplicity, with this Euclidean time as well as the usual position. And so this guy is defined to be the original operator. Now where its time is minus I TE, and the spatial part remains the same. And so if you just plug in these definitions into the equation we had above, you now see, and so I'm trying to be very careful here, just because it's important to be correct about all these signs. So I'm going through all these tedious details. And so if you just
I
plug
think you meant to say TE is IT, not minus IT, to be consistent with the rest of the book.
Okay. Yeah, maybe it's plus IT. Well, we can check after. I thought it was minus IT, but
But it's not consistent with the one that immediately after. But you want to say that T is minus ITE from the right? So
you're saying this would be a plus?
yeah.
Okay, great. It's a plus. Minus I x e phi of 0, comma 0, and e to the minus e0 t e plus I x t. Okay, so this is just plugging in that definition into the original definition. So now we have the Euclidean version. And so now we see that this Euclidean scalar operator here on the left-hand side is only going to remain invariant under conjugation if we define its conjugate. So this is a definition. So the definition of the conjugate of this Euclidean operator, as given by the symbol dagger, is the original Euclidean operator with now a minus sign put in next to the Euclidean. And so basically the point is very simple. It's just that because you've kind of like gotten rid of the I, by hand, thus if you want to make sure this equation still holds, you have to put the sign back in by hand when conjugated. And so this is something you have to be careful about when working in Euclidean space, which just follows from these definitions. So here I wrote this for a scalar operator for simplicity, but you could generalize this to a spinning operator. I won't show the details, but it follows very similarly. So for a spinning operator of spin L, which remember by definition means it's in the rank L traceless symmetric representation of the rotation group. So this guy, when you conjugate it with the dagger, it will equal, so these are thetas, U1, U1, UL, UL, and then you have the Euclidean operator, now with, again, the minus sign. And so the difference of spin, again, so like the scalar, you have this minus sign. The novelty of spin is you have these thetas, and these thetas are basically performing reflections in the Euclidean time direction. So they're defined as follows with these Kronecker deltas. So we choose our time direction to be the 0 direction. Okay, and so the point is that we see that unitarity in Lorentzian space corresponds, after doing our Rick rotation to Euclidean space, to a new reality condition in Euclidean space that flips the sign of t, and then also reflects all these indices. And so we call this reflection positivity. And so the main point of what we're discussing now is that unitarity in Lorentzian space becomes reflection positivity in Euclidean space. And so this is just a general statement about quantum field theories, which in particular will also hold for conformal field theories.
Sorry, you haven't said what's positive.
Sorry?
You haven't said what's positive.
Well, I mean, okay, so if what's positive is you take an operator, you multiply by its conjugate, you take an expectation value, that should be positive. That follows from conjugation, I would say. So this statement, in fact, can be proven both ways in something called the Osterwalder-Schrader theorem, which I will show no details for. There's some wonderful lectures by Slava, which are like 10 hours long, in case you want more details about this fascinating fact. But it's an important theorem mathematically. So one immediate implication of this fact is positivity of OP coefficients. And so this is an example of something which is easiest to show just in regular, Lorentzian, translational quantization. So this is something for which you don't actually use this funny quantization we introduced before. So in particular, if we consider a
Right.
3-point function,
Try the first.
Question?
yes,
Does it matter if you have like a vector or pseudo vector? Like should one be careful about?
you say for the definition of reflection positivity? You say the difference between a vector and a pseudo vector?
Or something like the reflection.
Well, okay. I mean, I'm only looking at certain specific representations of the rotation groups. I'm only looking at these rank L representations, and so I think you just have vectors. I don't think there are pseudo vectors.
Representation under the discrete part of the Lorentz or Euclidean group is it important or?
You're saying for a scalar versus a pseudo scalar, for instance? Good question. I don't know. Gee, do you know?
I don't think this cares well.
No.
I guess you could have no reflection symmetry, so then.
Well, I mean, it would be the same question of like, in general, Lorentzian quantum field theories, there's a difference between like a scalar and a pseudo-scalar in terms of conjugation. And I think the answer is no, and so I would think the answer is similarly no for this reflection positivity. Because it's a one-to-one correspondence between the two. So anything that holds for one should hold for the other. Okay, so back we were talking about. So now let's consider a 3-point function of 2 scalar operators. In general, I write scalars with this phi notation. So here's one scalar. Here's another scalar labeled by j at position 2. And then I'm going to put some general spin L dimension delta operator at position 3, sandwiched between the back two. So now if I take the conjugate of this, then let me also consider space-time points xij squared, which are positive. So basically I'm looking at space-like separated points such that these operators commute. And so when I take the conjugation, I just get the exact same thing back. And so now, but remember from the previous lecture that these 3-point functions are fixed by conformal symmetry to be proportional to something called this OP coefficient, labeled lambda I j omega delta L. So it was just this times a bunch of position dependence. But because the conjugate of this just equals itself, now using this well-defined notion of conjugation, this means that this guy must equal its conjugate, i.e. it must be real. So basically you can choose a basis of operators such that these OP coefficients are real, and at least these specific OP coefficients we're dealing with 2 scalars and an operator. I mean, there'll be other contexts where OP coefficients will be complex. But at least in this simple context, the OP coefficients are real, and this will be very important for the conformal bootstrap. And this is something you can show by defining conjugation, as we have just done. Okay, so far we've spoken about some simple applications of conjugation for the simplest quantization, which is just standard, just relativistic quantum field theory with slices that respect translation. Now let's explore implications of conjugation for this other quantization we introduced here, which I claimed is more powerful. And you'll see in a moment why it's more powerful.
Sorry, could you say again why the conjugation is the same?
Which
No,
conjugation?
the 3-point function conjugated is the same, and that's why you can argue that the OP is.
Okay, so the reason why it's the same is that we're looking at space-like separated points. These operators commute.
Oh,
And so then when you act with the conjugation and rearrange the operators, that doesn't matter. And then we know how the conjugation itself acts on each of these operators. It might like change a certain sign, but that doesn't actually affect the 3-point.
the choice of space-like separator is the choice.
Yeah. So it's important to choose space-like separated. You know, if we had been dealing with Euclidean space, and now with an immediate, but we wanted a Lorentzian space so that we could have these properties, which we claimed. Great. All right. That was exciting. Okay, so now let's consider how unitarity works in radial quantization. So first, just some introductory facts. So we can use the fact that radial quantization for a conventional Euclidean time quantization considered above, that i.e., the usual just R cross RD minus 1 quantization. So we can relate radial quantization to standard quantization by doing a while rescale. So the idea is that let's start with our metric. This is the metric on flat space. So RD. i.e. r cross rd minus 1, but it's Euclidean, so there's not really any difference between these two. So we can write this metric any way we want. We could write it just as, dx squared plus dy squared plus dz squared, but you could also write it using spherical coordinates. That's also allowed. And so let's write it using spherical coordinates in the usual way. So that means we have r as our radial coordinate, and then we have a metric on the sphere SD minus 1. So now let's just rewrite this metric by taking out this factor of r squared. So now we have dr squared over r squared plus ds squared sd minus 1. And now let's define r to equal e to the tau. So we're introducing a new variable tau. And in terms of this tau variable, we have e to the 2 tau times d tau squared plus ds squared sd minus 1. And so this, just by definition, is e to the 2 tau times the standard metric on the cylinder, which is r cross sd minus 1. So what we see quite explicitly is that the cylinder is related to flat space just by an overall factor, e to the 2 tau, which is another way of saying that they are conformally related. Because remember, a conformal transformation is something that changes the metric just up to some overall space-time dependent factor. So let's see how this correspondence works. So the idea is that we're going between this space and the space of a cylinder, and hilarity ensues. Okay, so for instance, how does a dilation in flat space, what does that correspond to on the cylinder? So a dilation is what sends r to just lambda times r. So all it does is dilate the radial direction, right? And so this guy on RD is identified according to the simple map r equals e to the tau by just shifting tau. So tau becomes tau plus log lambda. So we see that translations on the cylinder have a natural correspondence between dilations on flat space. And so this already should be a good motivation for why it's useful to go to the cylinder. Because maybe it's complicated thinking about dilations, but now we can just write it in terms of good old familiar translation. So this is just one example of a generator of conformal transformations. We can generalize this to the most general conformal transformation. So this was a formula given in the previous lecture. I'll just remind you what it looks like. So imagine we have a bunch of operators in various rotations, in various representations of the rotation group. And so these are defined, on a space-time with a certain metric G. Then after we do any kind of general conformal transformation, or in particular a Weil rescaling omega, so this is what it's called. It's called a Weil rescaling, where omega is e to the 2 tau. So then what happens to the correlation functions is that you get a bunch of these space-time factors, omega, which in our case is just e to the 2 tau, to the power of the scaling dimensions of the various operators we have. So again, this is again just quoting a formula from the previous lecture. So I will not derive it, because we already did not derive it in the previous lecture. And then here's the same correlation function. Now on a space-time where it has this extra Weil factor, which is just a certain kind of conformal transformation. So inspired by this conformal transformation, we are motivated to define cylinder operators. So the cylinder operator will have tau as defined there. And then it'll have this vector n, which is a unit vector on SD. So this guy is defined, the cylinder operator is defined as e to the delta tau times conventional operators on flat space, where x is identified with e to the tau times this unit direction. Okay, so now with this definition, correlation functions of cylinder operators are equivalent to those of flat space operators with these extra factors omega. And so these extra factors omega come from the definition. And so in sum, we've shown that radial quantization of operators on flat space becomes Euclidean time quantization of cylinder operators on r cross SD minus 1. And so our motivation for doing this is that we have a lot of intuition about how conventional Euclidean quantization works. I mean, that's the one we usually use. And so now we can just use that normal quantization on the cylinder, and that will automatically tell us facts about quantization in this scaling context in flat space. So let's see the first implication of this fact. So we just spoke about a moment ago conjugation. And we spoke about how that worked on flat space. So let's just map conjugation on flat space to the cylinder using this mapping we just defined. So remember, conjugation for Euclidean quantum field theory on flat space, say for some scalar, how did that work? So when you conjugated, you just got the scalar operator with a minus sign next to its time direction, which is what we identify with tau. But if we now translate cylinder operators to flat space operators, then we have this extra factor of e to the delta tau. And so that means that conjugation now in the cylinder context, after having mapped it back to flat space for the others quantization, the spherical quantization, will now tell us that our operators in flat space, when you conjugate them, so this is an operator on flat space, not the cylinder, this will have this extra factor of x to the minus 2 delta, and then also you have to invert these space-time dependence. Great. And so what we've learned is that conjugation in this scaling quantization is actually the action of an inversion on the operator. Because remember, this is how we define inversions. You take a space-time point and you divide it by the magnitude squared. So I've showed you explicitly how this works for scalar operators, just because it's very easy to see how this directly follows from these definitions. But as you can show for yourself, you can prove an analogous formula for spinning operators, and again, you will just find that conjugation in this choice of quantization is an inversion. And so remember that we had our 4 generators of conformal symmetry, right? We had translations, rotations, dilations, and something called the SCT, special conformal transformations. And remember, these SCTs, they were just defined to be a translation, and then an inversion, and then a translation. And so because conjugation, we've just shown, is an inversion, and because the SCT is basically just defined to be an inversion, that implies that if we conjugate translations, by definition, that will be the generator of SCT. Because the SCT just is the conjugation of an inversion by a translation. And so thus we've shown explicitly, using this funny scaling quantization, that in this choice of quantization, the conjugate of the translation generator is the special conformal transformation generator. And this is a very powerful statement, which we can now use to derive what are called unitarity bounds. So is it clear to everybody where this statement comes from? I mean, so one thing I want to emphasize, because this is something which at least I personally was not aware of when I first learned quantum mechanics, maybe the rest of you guys were, is that notions such as conjugation in reality depend on what choice of quantization you have. So like, because oftentimes you first learn about conjugation, you're like, oh, I know what conjugation means. It just means you make I become minus I. But that's not actually true. I mean, conjugation in the mathematical sense will change depending on your quantization. And so as you see, for this funny choice of quantization we're using now, it turns out that conjugation implies that one generator becomes another generator, which would not have been the case if we had chosen a different quantization. And so what I'm about to prove, in principle, you could prove with another quantization, but it would probably be much more challenging. And
maybe I can just clarify on the terminology, because I think you're using the term quantization in a slightly non-standard way. Because usually when we see the word quantization in textbooks, it means to turn classical system to quantum system. That's not what you mean at all, right? When you say quantization, what you really mean is that in quantum field theory, when we speak of local field operator phi of x, if you want to view that as linear operator acting on Hilbert space, there are different choices of Hilbert space on which this thing can act on. And the Hilbert space can be associated with different slices, say Euclidean spacetime.
yeah, I'm using quantization to mean my choice of Hilbert space. So perhaps this is a more specific version of quantization. So basically the statement is just that like there's infinite choices of Hilbert spaces. You could find any one you want, and like you want to choose one that respects the symmetries of the theory because that has advantages. In relativistic quantum field theory, the Hilbert space you use is just the simple one that respects translations. But in our scale invariant quantum field theory, we are choosing a different Hilbert space which is useful for other purposes, which I'm now explaining.
Just to say it slightly differently, but equivalently, phi of x, if you want to view that as linear operator acting on some Hilbert space, conjugation is only defined provided you specify the inner product on the Hilbert space. So for different Hilbert spaces with different definition of inner product, you have different definition of permission conjugation.
Okay, great. So any question?
So, should I always have this cylinder picture in mind when I talk about, because you kind of started just drawing concentric circles,
Yeah.
and you define states that way, but now you kind of go to the cylinder. So should
Yeah,
I
the reason I
always
would-
have this in mind or not?
Well, it depends what you want to do. I mean, the reason why you go to the cylinder is that, like, it's the intuition about the standard, time translational invariant quantized Hilbert space is the one which is kind of easiest to do calculations in. And so that's why it's useful to go to the cylinder. In principle, if you were clever enough, you could probably do everything maybe directly, without using the cylinder operators in flat space using that quantization. I mean, I'm sure people have done that as well.
They're mathematically equivalent.
Yeah,
Just
yeah,
change
they are.
variable.
Yeah, it's just a different picture. It's
And maybe one more question.
Yeah.
So that formula about omega squared g that you wrote.
yeah,
So let's say we are in two space-time dimensions.
yeah.
Is that only true for primaries or it's true for quasi?
Oh, okay. So I'm always talking about. Okay. So first of all, in these lectures, I'm always talking about primaries unless otherwise mentioned. So your question, and I'm also always talking about global conformal symmetry. So in 2 dimensions, there is a bigger conformal group, Virasoro symmetry. I'm not talking about that. So everything I say holds even if you just restrict to the global subgroup. So that means in 2 dimensions, this would be SO2, 2. If you furthermore want to talk about Virasoro primaries, you can say even more powerful statements, but that's not necessary for this.
But you are not in flat space now. You are going to the cylinder, right?
Sure.
Like
Yeah.
say the stress energy tensor, right?
Yeah.
Transforms.
Yes.
Gets like an extra piece.
Yeah.
In 2 dimensions when you go to the cylinder.
So this statement holds regardless of these anomalies. So like you have to be careful, but you can show that the statement holds even in even dimensions, even when you have anomalies, and it holds in the exact same way. So it doesn't change due to anomalies. So that's a good question, and the answer is that anomalies don't change. And this is something which can be shown, which isn't obvious. There's a footnote in my lecture. Okay, so now let's show the first application of this surprising fact: the conjugate of the translation generator is the SCT generator. So let's consider an operator O, labeled by A, which we normalize such that, because remember operators correspond to states. So if we're looking at these states corresponding to these operators, let's normalize it so that it's just a Kronecker delta. So we want our operators to be orthogonal. And this operator can transform in some representation of the rotation group, which will act as usual with the matrix S, as we discussed before. And so, as Shai was emphasizing before, when you talk about conjugation, you're really talking about reality. What's the thing which is real? Well, of course, it's A conjugate A, expectation. And so let's see implications of this reality. So let's consider the positive definite norm, which is the generator P acting on our operator OA, conjugate squared. So this thing has to be real. And so let's unpack this definition and see what this teaches us. So first of all, this thing just by definition is P nu acting on our operator OB and P nu acting on our operator labeled by A, conjugate. So I just unpacked what this thing means. Next, we can use the fact that the conjugate of P is K, which was, remember, the whole motivation for everything we're about to do. So that's the non-trivial fact. So this K now appears from what used to be the conjugate of P. Next, we can write K times P as actually the commutator of K with P. And the reason why we can do that is that these are primaries, and so that means K kills a primary by definition. And so that's why we're able to just turn this into a commutator. Sorry, this should be a P. And then finally, in the previous lecture, we defined how a commutator of the various generators, like what they are. And so we just use that definition from the previous lecture, acting on a state, and we find that we get 2 delta. We get these Kronecker deltas because these states are orthogonal, as I defined above, minus 2, and then you have this S matrix. Remember, the S matrix is always just the matrix corresponding to rotations for the specific space-time rotation group where these operators And so we've shown that this quantity must be greater than or equal to 0, just because this norm had to be strictly positive, or 0. And so, based on this, we thus learn that the scaling dimension of the operator must be greater than or equal to the maximum eigenvalue of this generator of the rotation for the specific operator. So the next step we have to do is we have to compute the eigenvalues of this operator S. So you can find that exercise in the lecture notes, but I will just skip it because I don't think it really teaches too much. It's basically a standard application of this trick, which I'm sure you guys have seen on tests before, where it's like if you have two operators like L and S, you rewrite them as L plus S squared minus L squared minus S squared, which I remember for quantum mechanics is like 25% of all homework questions. So you apply that standard trick, and what you learn, after going through all these tedious details, which I will skip, is that the scaling dimension is greater than or equal to the spin plus d minus 2 in the case where the spin is greater than 0. So remember, again, spin is the rank of a rank L traceosymmetric representation of SOD. And so this is called the unitarity bound. And these guys are very important. So this is something special to conformal symmetry, which you could only use because you have these conformal generators. And you see that the scaling dimension is bounded. You can also similarly derive a bound on the spin 0 case. So in that case, you have to look at positivity not just of the lowest norm, but also the second lowest norm, which is p squared, acting on this operator. And so the fact that this guy is positive gives an even stronger constraint if you trace through a similar argument, which is that delta has to be greater than or equal to d minus 2 over 2 when the spin is 0, with the exception of the case of the unit operator. So delta is 0 for the identity operator. And so you could ask, okay, do I get further bounds by looking at further descendants? So if I act with pq, p to the 4, and the answer is no. So the fun ends there, at least for this simple class of representations I'm looking at. Now, I just want to remind you guys again, these are not all possible representations of the rotation group. So for instance, you could look at fermions in 3D. You could also look at other operators in 4D and all kinds of weird representations, like 5 indices on the left, 2 on the right. And those will also have their own unitarity bounds, which will be slightly different from the ones I'm listing here. But for the purposes of these lectures, these are sufficient, and these honestly cover the cases most people care about. So these are the unitarity bounds, where d is the dimension of the space. Okay, so what happens when we saturate these bounds? So let's start with the scalar case. So let's imagine that delta equals d minus 2 over 2. So based on this derivation, that implies that this norm just equals 0. So this means p squared acting on the scalar operator is 0. But what is p squared? Well, in a certain representation, it's just delta squared acting on the operator. And this is just the Klein-Gordon equation. And so you can see that the Klein-Gordon equation for on an operator that saturates the bound, which is i.e. a free theory, just pops out of this formula. And so this might be a little surprising, because usually when you learn about the Klein-Gordon equation, it's very much a Lagrangian statement. So you write down some Hamiltonian or Lagrangian, you apply the Netter procedure, and out pops the Klein-Gordon equation. But everything in these lectures is without Lagrangians. I mean, that's the whole point. These are all about non-perturbative axiomatic statements. And so as you see, the Klein-Gordon equation does not require a Lagrangian. It's just a fact that if you have an operator whose scaling dimension is d minus 2 over 2 and is a scalar, then it satisfies the Klein-Gordon equation. So I thought that was cool when I first learned. And so similarly, you could look at operators that saturate the bound in the spinning case. So if delta equals L plus d minus 2, where L is now greater than 0, then again, based on how we derive this statement, that's the same thing as saying that p mu acting on the operator O mu is 0. And this is another way of saying that this operator is conserved, right? Because remember, P mu is the same thing as delta mu. And so you see that also the definition of an operator being conserved is identical to the fact that it saturates this band.
Mu is one of the L indices.
Sorry?
The O is supposed to carry L.
Yeah, sorry. I'm being a little concise here. There should actually be L of these guys. And there should only,
No,
oh, no,
only
yeah,
one.
so sorry. Yeah, there's only one. Yeah, sorry. Yeah. So you contract one of these guys, and then the other ones remain uncontracted. Yeah, so, yeah, because you're taking derivative of just one of these. Not dealing with more complicated ones. Okay.
L is used that P mu is related to the derivative operator, even now that P mu
Yeah.
dagger is equal to K mu. This radio quantization is
Yeah,
weird.
well, yeah, because I mean, this is just a certain representation. I mean, like this is just how generators act on functions of spacetime. So I mean, like that's just a kinematic fact. You know, like that doesn't depend on the choice of your quantization of your relative space.
I mean, well, once again, what the dagger means depends on your choice in a product. You cannot tell what the dagger is looking at the form of differential operator.
Yeah, I mean, it's kinematic. Okay, so let's give examples of these conserved operators. So first, let's consider an operator with spin 1. And so we will define the notation J mu is just this operator with just one index. And this is a conserved current. And so what we've just learned is that the scaling dimension of this J is d minus 1. And so this is what's called a conserved current for a global symmetry. So for instance, in the ON model, you would have a conserved current corresponding to level of symmetry, ON. You would not have a conserved current for discrete symmetries, such as the Ising model, which only has Z2 symmetry. So this is kind of an important difference, is that when you have a global continuous symmetry, you know that a certain operator must exist, but if you have a global discrete symmetry, you don't know that there's some specific operators that have to exist. This is why discrete symmetries can be harder to deal with and are slightly less powerful. Okay, so that's one example of a conserved operator. Another example of a conserved operator of spin 2, so this is spin 1. So for spin 2, so now we call this operator T mu nu, and this thing is just defined to be, O mu nu, where it's traceless symmetric as usual. And so this guy, by definition, its scaling dimension is just D. And so this is what's called the stress tensor operator, which is conserved. And every local CFT has to have such an operator. So you could ask, okay, what about conserved operators of higher spin? So it turns out that if the spin is greater than 2, and we have a conserved operator, then the theory is free if D is bigger than 2. So in any space-time dimension bigger than 2, if you have conserved currents bigger than 2, then you will have a free theory. And so this is a surprisingly non-trivial fact to prove. It was proven probably only in the last 20 years. And the fact that it's surprising is that it's not true when D equals 2. So in 2 dimensions, we know many conformal field theories which have conserved spins of all kinds of spin, and nonetheless the theories interact. So a classic example would be like a model of Wn symmetry. So like if you have Wn symmetry, that means you have some conserved current of spin n, and it's an interacting theory, even though it has these higher spin conserved currents. So this is something special to higher dimensions bigger than 2. Okay, so I just said a moment ago that having a spin 2 conserved operator, i.e. the stress tensor, is equivalent to calling something a local CFT.
Question?
Yes.
So this statement about higher dimensions?
Yeah.
When you say free, does it mean that the spin 2, the high spin current just decouples from everything, or?
Well, I mean, it means that your theory will have to have a part of it which is free. I mean, in principle, you could have product theories. So it's like you could have some theory which is like a product of 5 theories, 2 of which are free, 3 of which are interacting. But I guess, the moment you notice that there's an operator with dimension, D plus D minus 2 plus L, that means there is at least some sector of your theory which is free. There could be other sectors which aren't. So that's a good point, because sometimes it's not so obvious, if there's many, stress tensors within the theory.
Under assumption there's a unique spin 2.
But basically, the way you count the number of CFTs is how many stress tensors. So the idea is that, like, if you have 5 stress tensors, then it could be like 4 of them are free, 1 of them is not. Okay. So we just said that when you have one of these stress tensor guys, you call this a local CFT. And so when you have a local CFT, then you can can define a charge Q using the infinitesimal generators of the conformal group. So here we take an integral over some region sigma, which will include this operator. So we're taking an integral over this spherical region. Epsilon is the infinitesimal generator corresponding to Q. So these are things we defined in the previous lecture. I'll give an example in a moment to remind you guys. And then we put our stress energy tensor within this integral, and this defines these generators Q. So in particular, this epsilon is just some small parameter E nu contracted with a solution of the conformal Killing equation. So this is one example of a solution. So if in the case of dilations, this epsilon nu would just be x nu. So this is for dilations. So for the example of dilations, you set epsilon nu to just be x nu. And then, applying this formula, this means the generator of dilations, d, you could define it locally as an integral over this region sigma of, so here we have x nu, and then we have t mu. And so we see that we're able to define the generators of our conformal transformations as integrals of the stress energy tensor. And so the power of this formula is that, as you guys will show in the problem sets you are diligently performing, if you can apply this formula to the following 3-point function, so imagine we have two scalars, as well as the stress energy tensor. So if we apply that formula, which we just derived, to this 3-point function, then you will see that this allows us to relate the OP coefficient, which shows up in this 3-point function. So two scalars and P. So this OP coefficient will end up being related to the scaling dimension of these scalars phi, sprinkled with, D is just the space-time dimension. And then SD is just the volume of the sphere. Okay. This is with the canonical definition of the stress tensor. And so the canonical definition of a stress tensor is that if you take its 2-point function, I'm dropping all indices, it's going to equal some quantity which is called CT, and then a bunch of x dependents. Oftentimes, though, in the Bootstrap and in these lectures, we want to give unit normalizations to 2-point. And so instead of this canonical definition of T, we could define another quantity, which I'll just write as OD, 2, which means it has dimension 2 and spin 2. And this guy, you define as just the stress tensor, but you factor out some factors. So in particular, you factor out the sphere as well as the square root of CT. The reason why we do this is this implies that the 2-point function of this unit normalized stress tensor is 1, which is a more useful normalization. And then, if we consider the OP coefficient,
What happened to the factor of SD?
I'm not being careful about those factors. I'm only talking about whether the CT. Everything else is just kind of a more silly normalization. So this implies that this OP coefficient of the unit normalized stress tensor with two scalars, but basically let's drop all unimportant factors, is proportional to delta phi over square root of CT. And so this is a very important formula, because this CT, which is the coefficient of the stress tensor 2-point function, this counts the number of degrees of freedom in a conformal field theory. So for instance, when you're talking about conformal field theories in the context of quantum gravity, so like say for n equals 4 agreeing mills, this CT would be proportional to n squared, where n is the rank of the gauge group. And this is something generic. So usually like for any gauge group where you're in the adjoint, it will go like n squared. And so this C is kind of the degrees of freedom, and there's a way of abstractly putting CT into local data, because it's inversely proportional to this OP coefficient. And so this will be important once we start talking about bootstrapping things, as we will soon do. Okay. Now, this statement we just did, we can only do for a local CFT, which is a CFT which has a stress tensor. Now you might say like, okay, aren't those all CFTs? and this is a matter of definition. Maybe prior to the Bootstrap, people would have said, okay, that's everything. But we actually find it useful to discuss CFTs that are non-local. So i.e. CFTs, but non-local in a specific sense. So they are local in the sense that like they're defined by operators defined at a given space-time point. They're just not local in the sense they don't have a stress tensor. And so a classic example of a non-local CFT in this specific definition of non-locality. So a non-local CFT is something called a generalized free field theory. So a generalized free field theory is a theory which is just generated by composites of a given operator where you just add the dimensions. So it's non-interactive. And so imagine you have some operator O, a scalar, and imagine that the dimension of this O is